Thank you very much. I thought of it before and then I totally forgot. Okay. So when we're told that the tangent of A is 5/2, it means that we can draw a triangle, a right triangle. Here's, let's call this ABC, where the tangent is 5/2, means the opposite side, the tangent's opposite over adjacent, the opposite side I can pick to be 5, and the adjacent side I can pick to be 2. Now, here's my A. So my opposite, this is my opposite, is going to be the 5. This is my hypotenuse, because it's across from the right angle. We don't know, because we were given tangent, which is opposite over adjacent. This is my adjacent side, so that I'll pick to be 2. Notice then the tangent of A is 5/2. Now, I was asked to find the cosecant of A, which we said is the reciprocal of the sine. So I need for the sine the opposite and the hypotenuse. I have the opposite, but I don't have the hypotenuse. So the first thing I have to do is figure out what the hypotenuse is by doing A squared plus B squared equals C squared, which will give me 2 squared plus 5 squared equals C squared. This is 4 plus 25 equals C squared. So C squared is 29, which means that the C is the square root of 29. Okay, so now we have all 3 sides of this triangle. We can now do the cosecant of A. The cosecant of A is hypotenuse over opposite, because it's a reciprocal of sine. So it's the square root of 29, that's the hypotenuse, over the opposite, which is 5. And this is my answer in simplest radical form. Notice I don't have to simplify the radical. I can't do anything with the square root of 29, and there's no radical in the denominator. That would be your answer in radical form. If you wanted to find what that was in decimals, you'd have to do the square root of 29, and you'd have to divide that by 5, and you get 1, in decimals, you get 1.077 if you want to go to 3 decimal places. But most of the time, they're just asking you to give the answer in simplest form, which means leave the radical. Okay, so that takes care, that was what a review of what we had done in trigonometry. We had started talking about the chapter, which is actually the last chapter we're covering this term, and that is the chapter on exponential and logarithmic functions. And that's what we were going to be talking about today. And we did mention that how to solve, this is what's called an exponential equation. It's called an exponential equation because the variable, the unknown, is in the exponent. The base has to be a positive number. And right now, the only way we know how to solve these type of exponential equations is if we could get both sides of the equation in terms of the same base. This number, this is written in base 5. It's 5 to the 3x minus 1. Can we write the other side, the 125, in base 5 as well? Can we write that in terms of 5 to an exponent? And if I think about it, 5 times 5 I know is 25, and 25 times 5 is 125. In other words, if I multiply 5 3 times, I get to the 125. So I could write the 125 as 5 to the third. Right now, we can only deal with these type of equations, of exponential equations, where both sides can be written in terms of the same base. Once you have the same base, then it's easy to solve the equation, because if the two bases are the same, the exponents have to be equal as well. So the 3x minus 1 would have to be equal to the 3. This exponent equals this exponent because they're both base 5. And all you have is a simple equation to solve. You add 1 to 2. You get 3x equals 4. And that gives you that x equals 4/3. And I see, Reggie, you had both of those answers. Very nice. Okay, so this is pretty much where we had left off last time. And I'd like to continue from here. Let me also mention I did, our SI leader, Shireen, is no longer available for our class, but a new SI leader has been assigned, and I sent you out his schedule. And if you have any questions, especially now towards the end of the term, and there might be topics that you would like to review, either send me an email and I will take time in class to review that topic, or go online. I sent you the link, and you can, he will help you with any problems that you have. So today I'd like to start talking about something that's called logarithms. It's a strange word, but you're going to see it really is just a new way of looking at something you already know. We're used to writing things in terms of exponents. For example, I can write 8 squared equals 64. And we know what that means. It means if we take 8 and raise it to the exponent 2, which means multiply it by itself, we will get the answer 64. And we've talked about exponents, and we've even talked about the different types of exponents we can have. We can have regular whole numbers as exponents. We could have an exponent of 0, which means that the answer is going to be 1. We can have an exponent that's negative. And remember, when we have a negative in exponent, it means that we have a fraction. We're going to be taking a reciprocal. And we can even have fractional exponents, and those mean take radicals. So we talked about all the different types of exponents we can have. This is an expression that's written in exponential form. I can write this exact same expression in something that's called logarithmic form. It's written this way: log, that stands for logarithm, subscript 8, which means your base is 8, 64 equal 2. If we look upon the word logarithm as meaning exponent, this statement will make a lot of sense. The logarithm, which means the exponent, that you put on base 8 to get 64 equals or is 2. Notice how you're saying the same thing, but you're focusing differently. Here I'm giving you, and I give you something like this. I give you the base, the 8, and I give you the exponent. That's the way we're used to seeing exponential expressions. Given the base, give the exponent, and we usually try and figure out the answer. 8 to the 2, oh, the answer is 64, because 8 to the 2 is 64. Here in logarithmic form, I'm still giving you the base, but my focus is I have the base, I also have the number. What I want to figure out is the exponent. In other words, I'm giving you the answer, and I'm trying to figure out the exponent. So since we're looking at this, we're coming at these two problems from two different angles. It's the same problem, but here we're starting with the exponent, the base and the exponent. Here we're starting with the base and the number, looking for the exponent here. Let's just write down the rule for switching from exponential form to logarithmic form and vice versa. Here is an expression in logarithmic form. Log base b of a equals c. Listen to how it's read. Log, which means logarithm, log base b. The subscript is the base. Log base b of a equals c. Means that the base b raised to the exponent. Remember, log means exponent, so the number on the other side of the equal sign is the exponent. B to the c equals a. I would say a third to 1/2 of the questions that you're given on the final exam about logs really could be answered if you just switch from the log format to the exponential format. Let's take some examples. Number 1, what if I gave you a question that looks like this? If you notice, there are 3 main numbers involved in a log expression. There's the base, there's the number itself, and the value it's equal to, which is the exponent. Let's switch this from the log form to the exponential form. Again, the subscript is the base, so in this case, that's 7. The exponent is the number that's the other side of the equal sign. It's what the log is equal to. Log means exponent. Exponent equals -2. My exponent is -2. And that equals the number that's written right next to the word log, 1/49. This is the log format. This is the exponential format. Notice it probably makes much more sense to you when you look at it in exponential form, because what does 7 to the -2 exponent mean? Well, we know when a negative exponent means you put 1 over the number, and 7 squared is 7 times 7, or 49. So that 7 to the -2 does equal 1/49. Again, this was just a question of switching from the log format to the exponential format. That could be one type of question you could be asked about in logs. You could also be asked to solve an equation that has logs in it. For example, suppose I give you an equation that looks like this. Log base 3 of x is 4. What if I asked you to solve that equation? Well, as I said, most of the questions that have to do with logs are solved most easily if you go from the log format, which is very confusing to look at, to the exponential format, which is much more familiar. So let's put this in exponential form. Again, remember, the base, the subscript, that's the base that gets the exponent. The exponent is a number that's on the other side of the equal sign, what the log is equal to, which in this case is 4. And that equals the number that's right next to the word log, which in this case we know is x. So this equation in logarithm form becomes this equation in exponential form. Remember, they're just two formats of the exact same expression. They're telling you the same information. Of course, now this is easy to solve because we know how to do 3 to the 4th. 3 to the 4th just means 3 times 3 times 3 times 3, which equals 81. Again, as I said, most of the questions that are, or at least half of the questions on logs, can be answered if they're just put in exponential form. Okay, let me give you a couple to try yourself before we go on to anything else. Here's one question. And here's another question. Okay, while you're doing those two questions, I'm going to take attendance. Maury Alabre, Chelsea here, Ariana.
I'm here. Hello.
Hi. Okay, hi, and Chelsea, I see that you're here also. Okay. Adina.
I'm here.
Hi, how are you? Lachey.
I'm here.
Hi.
Hey.
Cave, I know you're here because you're always here nice and early. And Terrence.
Here.
Hi, how are you? And Karide, I see you answered already. Kizia? Hi, Kizia. Okay. And Lori, I see that you're here as well. Okay, got you. Faith. No problem. Ethan. Hi, how are you? Isabella. Serenity.
Here.
Hi.
Hi.
Reggie. Reggie, I know you're,
Sorry.
yeah, I know you're here. Hi. You're always answering my questions. Thank you very much. Zamia. Brandon.
Here.
Hi, Brandon.
Hi.
Michaela.
Here.
Hi. Seraphine. I know you're here, Seraphine, because I saw you before. Marissa. Sky. Hi, Marissa. Okay, got you. Renee. Hi, Renee. Sky. Jaden. Kennedy. Felicia. Hi, Felicia. Natalie. Hi, Natalie. I see a bunch of people are already sending me the answers. Michael, I saw you answered already that you're here, Michael. Cassidy.
Here.
Hi, Cassidy. Megan. Hi. Kalia. Kalia Watson.
I'm sorry, but Sky Powell is here.
I'm sorry.
Sky Powell is here. I sent you a private message regarding my situation. I'm sorry.
Okay. Lauren.
Here.
Hi, Lauren.
Hi.
And Kayla Zachary. Okay. Oops. Okay, and Sky, I see you're here. Okay, so let's do these two problems and continue from there. Okay, number one, again, we said what we're going to do, and this usually my first instinct is to change from the log format to the exponential format. And here my base I see is 10. The exponent, of course, is the number that's on the other side, which is 3. So this is 10 to the 3 equals what's next to the word log, which is the 5x. And now this becomes just a regular equation to solve. So 10 to the third, I can always figure out 10 times 10 times 10 is 1,000. When it comes to tens, the exponent of 10, the exponent tells you how many zeros there are. So 10 to the third means 1 with 3 zeros. So this is 5x. And of course, to figure out what x is, I just divide both sides by 5. And yes, the answer is 200. And a few people did give me that answer, 200. So that was excellent. Okay, so now let's look at this second one, which says simplify log base 9 of 81. Now, remember I told you when you have a log expression, you really are supposed to have 3 numbers. I have 2 numbers here, but there has to be equal to something on the other side. Now, I don't know what it's equal to, so I'm just going to call it x. I'm going to change this to log base 9 of 81 equals x, and I'm going to try and figure out what that x is equal to by changing this from the log format to the exponential. Again, my base is 9, because that's a subscript. The number on the other side of the equal sign, which is what we don't know, is x, is the exponent, and that equals 81. Well, now this is quite easy to figure out. 9 to what exponent gives me 81? I think everybody will agree that the exponent of the x has to be equal to 2. So the answer to this equation is just, or this expression is 2, not log base 9 of 2. Again, if you think about the word log meaning exponent, the exponent that you put to 9 to get to 81 has to be equal to 2. Talking about this one, where the base is 10. Actually, our whole number system is based on 10. And as a result, the most common number that's used as a base is 10. It happens to be easy because, remember, the log is the exponent. The log of, let's say, 1,000 would be 3 because there are 3 zeros. So actually working with logs where your base is 10 is probably one of the easiest numbers to work with. In general, working with powers of 10 to different exponents is easy because every time you multiply by 10, you're just putting in another 0. It's not hard arithmetic. It's like if you want to do 8 to the 4th power, you have to actually do 8 times 8 times 8 times 8. But if you want to do 10 to the 4th power, that's easy. It's a 1 with 4 zeros. The exponent and the number of zeros is always the same when your exponent is a whole number. So in general, working with base 10 happens to be the easiest and probably makes the most sense for us if we're trying to work some things out. Now, you're going to notice, if you look at your calculator, that you will see a button that says LOG on it. It might look like, it's not an IOG, it might be just a straight line, but that means LOG. There is a log button, a logarithmic button on your calculator. It happens to be the log where the base is 10. They had to pick a number that would be easy to use. They picked, if I have to pick one, it's not like you can go do any base on the calculator. Some calculators you can, but on a general scientific calculator, if you go to the log button, it will specifically be in terms of log base 10. That is what's called a common logarithm. Base 10 is the common log. I say I'm dealing with a common log. It's not that I'm just saying, oh, it's common and I do it a lot. It really specifically means the logarithms where the base is 10. And it's used most often as, again, on calculators, and very often in other situations, it's used so often that you might see something that looks like this. It says log base 1000. And it won't even have a base written in. It's not that the base was forgotten. It's understood that if the base is 10, you don't even have to write it on. Anytime I write the word log and I don't put any base there, I don't put a number there at all, no subscript, it means really that you're dealing with log base 10. And if you try to do this, let's call this x. That would be 10 to the x is equal to 1,000. You would see the x would have to be equal to 3 because 10 to the third is 1,000. And if you press your log button on your calculator and you do press log and you put in the word, put in 1,000 and you press equal, it will give you 3 because 10 to the third equals 3. So that's something we're going to keep in mind. If you ever see the word log written without any base, just remember the base is understood to be the number 10. It is what's called a common logarithm. So here's a question that was on a final. It says log of 2x minus 10 equals, a question like that. They asked you to solve this. And if you notice, again, it says log, so we really want to go from the log format to the exponential format, but I don't have any base written in. But I understand the base has to be understood to be 10. And if I change this from the log format to the exponential, it'll be my base is 10. My exponent, we know, is the number on the other side, which is 3, equals this number that's right next to the word log, which happens to be 2x minus 10. And now you just solve this again. 10 to the third is 1,000. And then I'll add 10 to both sides. So this will be 1,010 equals 2x. And then I'll divide by 2. And I'll get 505 as my x. So again, don't get upset if you see the word log and there's no base written there. The base is understood to be 10. And I'm going to now I want to go on and do some different types of demonstrations. And a lot of my demonstrations are going to involve base 10 because they're just the easiest ones to work with. But what I'm saying really applies to all types of logs. What we're going to be talking about now is what's either called logarithmics or properties of logs. There are 3 basic rules that apply to logarithms that when we talk about them, I think they'll make sense because as long as you remember what you're talking about when you're dealing with logs is the exponents. And the rules that apply to logs are really the rules that apply to exponents. So let's look at some of these rules. I'm going to give you some examples in real numbers, and from that, we're going to decide what these rules should be. So let's say I have this number x that I'll call 100. And let's call number y 1,000. Okay. Now let's talk about the log of x. What should the log of x be? Now, obviously, I didn't write a base here, so I'm talking about base 10. What should log of 100 be? Remember, let's call this out. I think if you change it to the exponential form, we'll just do it with this one. It'll be clear. The log of 100 means 10 to what exponent will give us 100? And obviously that n should be 2. Again, I keep telling you, when it comes to base 10, and these are easy numbers like 10 and 100 and 1,000, the log, the exponent, is just the number of zeros. In other words, the log of 100 is 2. Similarly, if I talk about what is the log of y, remember y is 1,000. What is the exponent that will give of 10 that will give us 1,000? Obviously, that's 3. 10 to the third is 1,000. So we know if we have in base 10, 100 and 1,000, the log of 100 is going to be the 2, and the log of 1,000 is going to be 3. Now, let's say I multiply x times y. I multiply the 100 times the 1,000. Obviously, I'm going to get 100,000. Now, what is the log of x times y going to be equal to that? Well, how many zeros do I have? 10 to what exponent will give me 100,000? I think it's understood that it should be 5. 100,000 is 10 multiplied by itself 5 times. So I want you to look. What is the log of x times y is 5. How does that relate to the log of x and the log of y? Even though I am multiplying the x times the y, when it comes to the logs, what I'm doing is not multiplying, I'm adding. I'm getting 2 plus 3, which is 5. But again, think about it. The logs are exponents. What happens when we multiply numbers? What happens to the exponents? We add them. So therefore, we have this first rule. First property, let me put it over here. Property number 1, the log base b of xy is equal to the log base b of x plus the log base b of y. When you are multiplying numbers, you add the logs. Again, keep in mind, logs are exponents. What about the second rule, the second property? Well, what if I do the log? Let me take some different numbers now. Suppose my x is 1,000 and my y is 100, and I divide x by y. What's going to happen? I'm going to have 1,000 divided by 100, and it's going to give me 10. Okay, let's do this with logs. What is the log of x? Well, we know the log of 1,000 is 3. What is the log of y? Well, we know the log of 100 is 2. So what is the log of x divided by y? Well, what's the log of 10? X divided by y is 10. What is the log? What exponent should I put on 10 to get 10? Obviously, the answer is 1. And again, we get this strange situation when I'm dividing the numbers. What I'm doing to the logs is not dividing them. I'm not doing 3 divided by 2. I'm doing 3 minus 2. But it sounds strange until I think. Remember, logs are exponents. And I know when I'm dividing numbers, what I do to the exponents is I subtract them. So here comes rule number 2. Log base b of x divided by y is going to be the log base b of x minus the log base b of y. Or think about it. Anything on top will be a positive log. Anything in the denominator, anything you're dividing by, is going to get a minus, because when you're dividing, you're subtracting the logs. One other rule. Suppose I take the number 100 and I raise it to the 3rd power, which will mean 100 times 100 times 100. I think everybody will agree it's equal to 1,000,000. Okay, let's talk about this in terms of logs now. We know that the log of 100, we've done this before, there are 2 zeros. I know that I have to do 10 to the 2 to get 100. The log of 100, when we're using base 10, and that's what it is, because I'm doing this demonstration all in base 10. The log of 100 is 2. So what is the log of 100 to the 3rd power? Well, that really means the log of 1,000,000. Because the 10 to the 3rd we know is 1,000,000. And the log of 1,000,000 happens to be 6. Because I have 6 zeros. Or if I multiply 10 by itself 6 times, I'll get 1,000,000. So if you look what happened, we took the log of 100, which was a 2, and we multiplied it by this new exponent 3. This was the 3 times the 2. That's what gave us the 6. In other words, this new exponent, the 3, gets multiplied by the 10 to the 2, the log, because the log itself is an exponent. If I wanted to write this in as a rule, here's what the rule is going to look like. This is my 3rd rule. Log base b of x to the nth power, so some exponent, is going to be equal to the n, the exponent, times the log base b of x. That's exactly what we did over here. We took the log of our x, which in this case is 100, which was 2, and multiplied it by this 3, which is this new exponent. That makes sense also in terms of logs, because the log itself is an exponent, and when you start with something, when you have something that is an exponent and you raise it to a second exponent, you're multiplying the two exponents together. But if I wanted to explain what to do in simple words, what it means is take the exponent and make it a coefficient. Take this exponent and move it to the front. These are the three properties of logs. They apply to logs, of any base. Again, I was demonstrating them with base 10 because they were easy numbers to work with, but it applies to any base. Now, how does that, what kind of questions could we ask that have to do with that? Well, first of all, I'm going to leave these up. Listen, I'm going to erase because I can't have so much on the word. I think you understand that already. Whenever we're asked a question where we're told expand,
Also,
let's say I gave you an expression that looks like this. Okay. Suppose they asked us to expand or write an expanded version of this expression. In other words, what they're asking me to do is to separate this into its separate individual rules. So here's what I do. I first look for anything that involves multiplication and division. Don't look at the exponents anyhow. In this case, there are no exponents. And I just make use of all of these rules that I have over here. So the first thing I see in this expression is I have two numbers being multiplied. The x times the y are being multiplied. What that's telling me in terms of logs, remember the logs are those exponents, that what I have to do to the logs is add them. So this will be the log base 2 of x plus the log base 2 of y. In this case, we're using log. The rules apply to no matter what base you use. You just have to make sure to apply. The only place that you don't have to put in the word log is when you're using log base 10. Otherwise, you have to put in the base. But since we have x times y, we know in terms of logs, when we're multiplying the numbers, we add the exponents, we add the logs. The next thing I see is that I have a, it's being divided by z. Now I know when I'm doing logs, division becomes subtraction. So this becomes minus log base 2 of z. So this is what's called expanding the expression in terms of logs. You use these three rules to tell us what to do to the logs if this is what we're doing to the numbers. We're multiplying the numbers and x and y and dividing by z. So that means in terms of logs, we're going to add the logs x and y and subtract it from the log of z. Notice I have to put the word log in front of each of them. Let's try another example. I'm going to do a couple more and then I'm going to give you some to try. Suppose I have a log base 7 of x, y to the third over the square root of z. And I want to expand it. Well, none of my rules here told me what to do when I have a square root. But we remember another way of writing radicals is by writing them in terms of fractional exponents. The square root of z is the same as z to the 1/2. In this chapter on logs and exponents, we never use the radical sign. If we have a square root or a cube root or anything, we change it to a exponent. The square root of z is the same as z to the 1/2. The cube root of z is the same as z to the 1/3. I'll go one further. The fourth root of z, for example, is equal to z to the 1/4. In other words, when no number is written inside the check mark of the radical, it means a square root and the exponent is 1/2. Otherwise, when you have these indices, if whatever the index is, that becomes the denominator of the fraction. So really what I'm asking you to do in this question, log base 7 of x, y to the third over the square root of z really means over z to the 1/2 power. So that's number one. That has nothing to do with exponents and logs. Logarithm, it's just that we only use exponents. We do not use radicals. Now I can expand this expression. Again, I look for anything that involves just multiplication or division. So I am multiplying these two numbers together and I'm dividing it by this. Again, anything in the numerator is going to be positive. Anything in the denominator is going to be negative because it's going to be divided by. So this is expanding this. I'm going to get the log base 7 of x plus, remember when it's multiplied, we change it to logs. When we have multiplication of numbers, we add the logs. So we're doing plus log base 7 of y to the third. And we're dividing it by z to the 1/2, which means that in terms of logs, we have to subtract log base 7 of z to the 1/2. So step 1, change multiplication to adding of logs, change division of numbers to subtraction of logs. Then go back and see if you have any exponents, because any exponents will become the coefficients when it comes to logs. Log base b of x to the n becomes n log base b of x. Well, this has no exponent, so I just leave that log base 7 of x. This y to the third has an exponent of 3, so I'm going to put that 3 in front, and that's going to become plus log base 3 log base 7 of y. And finally, this expression, the z, has an exponent of 1/2, so that 1/2 is going to become the coefficient minus 1/2 log base 7 of z. And this is how you expand this expression in terms of individual logs. Again, where there's multiplication of numbers, you add logs. Where there's division of numbers, you subtract logs. And where there are exponents of numbers, you make those exponents the coefficients. Because again, keep in mind, what you're dealing with when you're dealing with logs is exponents, and the rules that apply to logs are the rules that apply to exponents. Let's do another example. Okay, I'm going to give you a couple minutes to try this, to expand this. Again, notice I don't have any base here, so it means we're dealing with common logs, with base 10 logs. See if you can expand this. Okay, let's work on this together. Again, first of all, whenever I see a radical and the word log with it, I change that radical to an exponent. So this I'm going to rewrite as log. The cube root of x is the same as x to the 1/3 divided by z squared 1. And now I'm going to expand. Remembering where I have multiplication, I'm gonna add logs. When I have division, I'm gonna subtract logs. So I'm gonna get the log of x to the 1/3. That's everything that's in the numerator. And now I'm going to subtract everything in the denominator because I am dividing everything by the z squared y. So I'm going to do minus log z squared and also minus log y. Even though these two are being multiplied together, you could put it in a parentheses and subtract the whole thing. They're both in the denominator, so they both have to be negative. You were dividing both the x to the 1/3, both by the z squared and by the y. Don't make this a plus because then it will look like you're multiplying the x to the 1/3 by the y. These are, anything that's in the numerator will be positive, anything in the denominator will be negative. Now, I'm not quite finished because I still have these exponents. Remember, I take care of the first two steps, the multiplication and division. Now I go back. Any place I see an exponent is going to become a coefficient. So this is going to be 1/3 log x minus 2 log y. 2 log z minus log y. But notice these became the coefficients. Here's my x. So this would be my final expanded version. Don't forget that that log y, since it's in the denominator, has to be a negative. It has to be a minus in front of it because we are subtracting, we are dividing by it. Reggie, you'd have to put a 1/3 in front of this. You see that? And you don't have to put in the log base 10. You could just write log. Okay, let's do just one more thing, and then I'll let you go. We'll continue with it. And that's, what if I gave you an expanded version of this example and asked you to contract it back to the original? Let's do something like that. Suppose I gave you this. One half log base 3 of x minus 1/3 log base 3 of y minus 3 log base 3 of z. I am giving you this expanded version, and I want you to contract it back to a single log. I want it to be just log base 3 of something. Okay, so I'm going to do this in the opposite direction of the way I did the expansion. In the expansion, I first looked for the multiplication and division, and then I went to the exponents. So when I have the expanded version, I first want to go back to those coefficients and change them back to exponents. Make sure any number that's in front of the word log goes back to being an exponent. In other words, This really means log base 3 of x to the 1/2 minus log base 3 of y to the 1/3 minus log base 3 of z to the 3rd power. Any number that's in front, any coefficient goes back to becoming the exponent. Because that's what originally it was. After you've done that, you can then look for the additions and multiplications. Anything that's positive will go in the numerator of a fraction. Anything that's a negative will go in the denominator of our fraction, because the positive means you're multiplying, the negative means you're dividing. So that'll give me log base 3, just going to have one thing. The only thing that's going to be on top is the x to the 1/2, because that's the only one that's positive. And in the denominator, I'm going to have the y to the 1/3 and the z to the 3. Because those are both negative, means they're both being divided. The only thing that's left is that usually we don't leave our answers with fractional exponents. We change them back to their equivalent in radicals. So this will be read as log base 3. Well, the x to the 1/2 means the square root of x. Y to the 1/3 means the cube root of y times z to the 3rd. Now that's outside, these are not. And that's how your answer would be written as a single log. Again, it's just a matter, it's really like using a dictionary. These are your 3 words that you have to learn how to use. And it's a combination of all of them. But don't forget, take care when you're going back from the expanded version to the single log version. First, take care of the exponents, which are now the coefficients, and then do the multiplications and divisions. I'm going to give you one more to try, and then we're going to leave it at that. Okay, so let's see if I give you an example. Yeah, right, this is a single log. 2 log base 5 x plus 1/3 log base 5 of y minus log base 5 of z. I want this written as a single log. Okay, let's do this together. Again, remember when I want to go from the expanded version back to the contracted single log version, the first thing I look for are the numbers that are in front of the word logs. The coefficients have to go back to being the exponents. In other words, this will be log base 5 of x squared, because there's a 2 here, plus the log base 5 of y to the 1/3 power, because this is a coefficient of 1/3, minus the log base 5 of z. There's no coefficient in front of here, so we leave it. So that takes care of the exponent. Now we're taking care of the multiplication and division. So we're going to write log base 5. Remember, anything that's positive is going to go on the top. Anything that's negative is going to go in the denominator. So this is going to be an x squared, a y to the 1/3 on top because they're both positive. And then the denominator is going to go the z because it's negative. The only thing that we're left to do is change this y to the 1/3 to its equivalent. Well, this is log base 5, x squared, cube root of y, because that's what y to the 1/3 means, over z. And that would be your single log. We're going to see on Thursday how to apply this to solving equations that have logs in them, and how to and also how to do more difficult exponential equations. So that's what we're going to be finishing up with on Thursday, is solving exponential and logarithmic equations. And we're going to see how these rules are necessary for that solution. Let me just remind you that I'm not giving you additional homework on this because you have a test that has to be completed by Thursday on Delta Math, and there will be a test available on Blackboard starting this afternoon. I think after 2 is when I've scheduled it to start, that you should be able to, it's a practice final, but it's also a test that has to be completed. I'm giving you 2 chances to do that. Each you can do the test twice, and I will take as your better mark the mark for the test. Don't forget, we only have 3 more sessions before class is over for the term. The last class is December 9th. That's a week from Thursday. Also, I've sent you a link to an information about a new SI instructor. If you want any help, he will certainly be of good, he will be available to help you out at his given hours. As I said, I sent you the schedule and the link. Don't forget also that any missing homeworks or tests must be completed by the end of the term in order for you to get complete credit for all the work. All right, have a good day, and I will see you on Thursday.
Oh, good one, Professor.
Bye-bye.